Now, let's talk about the Brownian motion, what we actually mean by this, and what are the typical properties that are associated with the Brownian motion. As a word, it is typically named after Mr. Robert Brown, who has observed, he is basically a botanist. So, he has observed the movement of the pollen particles in water and whatever he has designed as a two-dimensional Brownian motion, it is showing some kind of resemblance to these pollen particles. And the stochastic, this has been combined with the stochastic processes, especially on the stock exchange, and that is where this concept of Brownian motion, stock exchange prices, that is where the concept of Brownian motion has come into the world of financial markets. Simply put, whenever I talk about a Brownian motion, any kind of movement, it's basically a stochastic process, first of all, in continuous time, continuous state. So any process which is operating in continuous time and a continuous state space, we call it as a Brownian. I mean, it's an example of a Brownian motion. So simply put, when I'm talking about a Brownian motion, especially as the example of stock prices, they keep changing every minute interval of time. So they are continuous time process. And the values, they are not just integers, they can change by any small tick size. So even their state space is continuous. So those kind of processes where we see a continuous time as well as a continuous state space, we are referring to them as Brownian motion. And in this Brownian motion, when we understand this concept of Brownian motion, we have two major categories to start off with. One is the typical general Brownian motion, and the other one we call as the standard, which is a special form of Brownian motion. Anything which we denote as a Brownian motion, right? Anything which we are denoting as a Brownian motion, typically I represent it with a process Wt, where for time, so this is the way, so this is nothing but the values that a particular process, here probably whenever I am talking about a process, you try to relate it with a stock price. Now the stock price at different points in time, right, at time period 1, time period 2, that is what we are denoting as a general Brownian process. And the more standardized term for a standard Brownian process is Bt. So everything else remaining the same, the notation is Wt here, the notation is Bt here. Now properties wise, any Brownian motion, whether it is general or standard, few things which we talk about, they are having independent increments, right? The increments means the change from one period to another period, Wt minus Ws, or Bt minus Bs, means if S is the older time point, T is a new time point, the value of the stock, let's say S is yesterday, T is today. The difference between the stock price of today minus the stock price of yesterday is not at all dependent on stock price of day before yesterday. So where T is greater than S is greater than R, I say that this increment, whatever has come out, it is not dependent on WR. It is not dependent on BR, which means the increments are completely independent. That is one major property of Brownian motion. Then the increments, apart from being independent, the increment should even be stationary. What do I mean by stationary? Whatever the Wt minus Ws that we are getting, it depends not on the values of Wt or Ws, it only depends on the time lag, T minus S. Bt minus Bs, even for a standard Brownian, it depends only on the difference between the T minus S. It does not depend on Bt or Bs. And from the world of stochastic calculus, we know that if any process is having independent increments, we even say that it satisfies the Markovian property as well, which is the value of if I'm looking at the conditional probability based on all the previous values, all the history of values, only the latest information is sufficient to predict the next information. So if I have to predict further time, the process for t plus 1, and I have x1, x2, x3, xt kind of processes known, the Markov property simply says this entire thing is reduced to just understanding the process xt, because xt itself incorporates all these things. So anything that is happening having an independent increment also is expected to follow a Markovian kind of a property here. And these increments, apart from being stationary and independent, we also say that they are Gaussian. Gaussian is another name for they follow a normal distribution, which means the Wt minus Ws, it follows a normal distribution with the mean as the drift times T minus S and the variance as the sigma square times T minus S. But the Brownian motion, which is the standard Brownian motion, which is a special form of a Brownian motion, wherein we see that this follows a standard normal distribution. That is what is the differentiator. So here there is no drift. So standard normal means the mean is 0. Mean times T minus S will still be 0. And sigma is 1. So this becomes T minus S. So that particular Brownian motion, which is having a drift of 0 and the variance, where this is the mean is called as a drift, and the variance of 1, which is otherwise called as a diffusion coefficient. So when these two are the case, the regular Brownian motion gets transformed into an independent, a standard Brownian motion. And in some terminologies, the standard Brownian motion is also called as the Wiener process. The standard Brownian motion also is called as the Wiener process. And standard Brownian motion is very important to understand because it also is looked at as a continuous version of the symmetric random walk. Simple symmetric random walk, which is actually a discrete version. The continuous version of it is typically being looked at as the standard Brownian motion. And one thing, there has to be a continuous sample path Either it is for a Brownian motion or for a standard Brownian motion, the whole path has to be continuous. There should not be any kind of a breaks in the middle. And in case I am looking at the standard Brownian motion, at time 0, the value of that process should be equal to 0. These are the things which are the typical initial properties that are associated with any kind of the Brownian motion, and the stock price movement is expected to follow all these things. The prices, the difference between today's price and yesterday's price is not dependent on day before yesterday's price. The difference between today's and yesterday's is only dependent on the time difference between these two periods, and it is not depending exactly on the values between the two periods. And the difference is going to follow a normal distribution with mean equal to mu times the time difference and variance equal to the diffusion coefficient or the volatility coefficient times T minus S. And stock prices follow a continuous sample path. So we could very well see that the stock prices are typically following a kind of Brownian motion. And here, by combining all these things, it is in a simplified form said Brownian motion is the only stochastic process which is having stationary, independent, and Gaussian increments and having a continuous sample path. So this is the property which is associated with the Brownian motion. And the standard Brownian motion can be looked at just like a standard normal distribution versus normal distribution, where the mean is 0 and the variance is 1. Here also the increments, if they are following a normal distribution with a mean of 0 and a variance of 1, we call that kind of a process as a standard Brownian motion itself. And there are quite a few other properties, right? Apart from the current properties which I have discussed, there are quite a few other properties that are associated with the typical standard Brownian motion. Now we have said the standard Brownian motion is depicted with Bt. Now the best way to solve majority of the properties is split it. Bs. Bs is the value of the stock or the value of the process at time S. Now what I'll do is I'll write it as plus Bt minus Bs. This is the increment part and this is the value at time S. Now this will make stuff for us to understand the different properties that are associated with the Brownian motion. So if I see some important properties, let's try to take the covariance between Bs and Bt. The covariance between Bs and Bt. Now if I have to drive that, probably I'll do it like covariance between Bs comma Bt. I am writing it as Bs plus Bt minus Bs. Now that gets simplified to covariance between Bs comma Bs plus covariance between Bs comma Bt minus Bs. Now we know covariance between Bs and Bs is the variance of Bs, and covariance between Bs and Bt minus Bs. These two are independent. If it is a Brownian motion, one of the properties say that the increments are independent. So the covariance between that is 0. And we know that the variance of Bs is the variance of Bs. We have seen that the normal distribution Bt minus Bs follows a normal distribution with a mean 0 and a variance T minus S. So same logic, if I am putting Bs, I will write it as Bs minus B0. This will follow a normal distribution with 0 and variance equal to S. So this is coming out to S. So in a way, the covariance between the Bs and Bt works out as the minimum of S comma T. Because here S is the previous period, we'll get the covariance as S. Otherwise, the covariance is going to work out to T. So this is one important property. The covariance between Bs and Bt is always the minimum of S and T, which is purely a factor of time. We have already talked about the Bt is a Markovian process. Because it has independent increments, we can very well talk about that particular process being a Markovian process. Similarly, we also say Bt is a martingale as well. What is this martingale? I'll talk about the expected value of Bt given the history up to the time period S. And this says they should be equal to Bs. That is what is the typical martingale. Now let me try it out whether I can do it. Bt, I'll write it as Bs plus Bt minus Bs given Fs. Now expand it. Expected value of Bs given Fs plus expected value of Bt minus Bs given Fs. Now first of all, this expected value is 0 because Bt minus Bs is independent of what all happened up to S, and it is following a normal distribution with a mean of 0. So this part is 0, and expected value of Bs given Fs is nothing but Bs itself, because there is no expected value. It is an actually known value. Bs is an actually known value up to time period S. So it is working out to Bs. So it can very clearly be seen that the Bt is a martingale in this process, right? And we can also see, if I am having another process, let's say B1, right? If I am having another process B1 of T, which is more like 1 by square root of C times BCT, then it says that B1 is also the B1 as a process. If it is of this form, the B1 is also a standard Brownian motion. Now I can very well check out this and prove it using the covariance concept. If the covariance between these two comes out to be the minimum of T and S, then it is fair enough. So the covariance between these two is nothing but covariance between 1 by root C times BCT, 1 by root C times BCS. And the covariance, we know it is 1 by C times the covariance between BCT comma BCS. And CTCS, we know it's a minimum of these two. If these two are the Brownian motion, it comes out as CT or CS. So the minimum of it, I'm taking it as CS, which will work out to S. So that means any process which is of this form, 1 by root C times BCT, it is also a standard Brownian motion. This is called as the scaling property of the Brownian motion. Any process which is 1 by root C times BCT also is a standard Brownian motion itself. And apart from that, Another important property that comes in this direction is the time inversion property. The time inversion property, what it says is, if I am having some b1 of t, which is t times b1 by t. The same logic you will use, covariance of b1 of t comma b1 of s. Same logic if I have to go, covariance between t times b1 by t, s times b1 by s. Now I can say st times covariance between b1 by t comma b1 by s. Now if these two are Brownian motions, I can very well say if these two are Brownian, the covariance between these two is simply the smallest of these two. S is lesser than t, so 1 by t is lesser than 1 by s. So I'll do it as 1 by t, which will again make this as s, which means b1 of t is again a standard Brownian motion itself. Right? So all these things very clearly are the various properties that are associated with a standard Brownian motion and a Brownian motion in general, and we should be able to apply these kind of properties as a part of various numericals. And a few more important things. The sample path, whatever the Brownian motion is typically giving, which is a continuous sample path, it should not be differentiable anywhere. It is not differentiable anywhere, which means it should not have a graph which has a well-defined slope. No well-defined slope at that particular point. That is where we are bringing in this important concept of the Brownian motion. The sample path is not differentiable anywhere. Right? So which is, in other way, if I have to put it, at any particular point t0, the probability that the sample path is differentiable, the probability that a sample path of a typical Brownian motion is differentiable should be equal to 0. Right? So this is one more important property that is associated with the typical Brownian motion. Now, a simple improvement over the regular Brownian motion is otherwise called as a geometric Brownian motion, which is more and more appropriate to the world of stock prices rather than the regular Brownian motion, which is considering all these facts. Bt minus Bs is independent of Br, is stationary, dependent only on T minus S. Generally, it is found that this entire kind of a situation is more and more applicable if we are looking at modeling for small time periods, because we are describing this as a normal distribution with a mean 0 variance T minus S. There is a very good possibility that the Bt in some cases may turn out to be a negative value. And I can't take Bt as the stock price here because stock price can never be a negative value. So this regular Brownian motion kind of a concept, the standard Brownian motion or a regular Brownian motion kind of a concept may not work for describing the stock market prices or indices in the long run, because there is a possibility that this value can become negative, whereas in reality the stock prices and the index values cannot be negative. And one more thing before we move further, we talked about a regular Brownian motion, we talked about a standard Brownian motion. If I have to convert this into, once I have a standard Brownian and I have to convert it into a regular, It's as good as I'm taking Wt as W naught plus mu T plus sigma Bt. This is the relationship that we are trying to build between the regular Brownian motion, general Brownian motion, as well as the standard Brownian motion. Now we'll use this relationship as well. Now when I talk about the geometric Brownian, we are making a small modification. We are representing it as ST. BT represents a standard Brownian, WT represents a general Brownian, and ST is representing a geometric Brownian motion. And it is the way we are writing it as e power WT. Means it's as good as e power W naught plus mu T plus sigma Bt. This is what is a typical structure of a standard Brownian motion, geometric Brownian motion. And we see that this is log normally distributed. The ST, we see that it will not be normally distributed, because when we say WT is normally distributed, e power Wt is log normally distributed, not normally distributed. So St is log normally distributed with parameters W naught plus mu T and variance being sigma squared T. Right? So the mean of this St is W naught plus mu T. The variance of this St is sigma squared T. And what we see is, because of this kind of a relationship, ST will always be positive, and that is where it becomes more and more appropriate to model the stock prices and indices. And so whenever we are trying to build in the expected value of ST, all it is coming out is e to the power of W naught plus mu T plus half sigma squared T, and the variance is coming out as expected value of St squared times mu squared into e to the power of sigma squared minus 1. So e to the power of sigma squared T minus 1 is becoming the, so we know that the once the parameters are these two, we can very well find out the mean as well as the variance of the standard norm of the log normal distribution. We know that the mean of a standard normal of a log normal distribution is e to the power of mu plus half sigma mu plus half half sigma squared, and variance is coming out as mu squared times e to the power of sigma squared minus 1. So this is what we are computing for the mean as well as the variance for that log normal distribution, which is the ST. But of course, we really need to understand now ST does not have any kind of independent increments. It does not have stationary increments. Only the WT and BT are going to have independent as well as stationary independent increment, because I cannot say ST minus SS is independent, or I cannot say ST minus SS is normally distributed. So we are not directly getting the increments to be independent or stationary. So anytime we are working with respect to a standard, geometric Brownian motion, we are first taking the logarithm of the application, whatever the prices or whatever the data, take the logarithm. Once you are taking the logarithm, it becomes normal, and once it is becoming normal, the increments are coming out to be Brownian. The increments are typically coming out to be independent and stationary following a Brownian motion. So then use all the techniques that are appropriate to the Brownian motion and then progress further. So instead of directly taking the stock prices as it is, take the logarithm of those stock prices and then go ahead in terms of working in terms of the Brownian motion rather than directly looking at the standard, the geometric Brownian motion data, because it does not follow any kind of independent increments or the stationary increments. So this is what is a brief overview on the typical Brownian motion, standard Brownian motion, geometric Brownian motion, the kind of different properties each of these motions carry out, and the typical applications for each of these different kinds of Brownian motions. All right.